Welcome to Lecture 2.1, Understanding and Applying Program Logic Models. First, let's begin by asking the question, why do we do program logic models? Program logic models are an essential part of conducting program evaluations and building performance measurement systems. Chapter 2 in the McDavid and Hawthorne book is the first of 4 chapters that lays a foundation for program evaluations that focus on program effectiveness. Chapter 2 is also the first of 3 chapters, chapters 2, 3, and 4, that serve as a foundation for developing and implementing performance measures. Program logic models are based on a metaphorical understanding of programs and the environments in which they are embedded. What is a metaphor? A metaphor is a figure of speech in which a word or a phrase is applied to an object or an action to which it's not literally applicable. Another definition is that it's a thing regarded as representative or symbolic of something else, especially something abstract. Models can be a form of metaphor. We don't expect a model airplane to do all of the things that a real airplane does. Many engineers, for example, in the automotive industry, create models of vehicles as they're trying to understand them and build them in order to better achieve those goals. For example, an automotive engineer might model the external parts of a car and place it in a wind tunnel in order to understand how much drag the car has, how the wind affects it, how that affects miles per gallon. In creating a model such as that, the engineer does not need to put in the engine or the seats or the radio or any of the internal parts. So you have to remember, when you're constructing a model, not everything that's out there is relevant. Not everything that's out there has to be put in the model. What's the relationship between models and metaphors then? Well, again, if we think about our program logic models, these are things that are representative or symbolic of the program themselves. I've given you there on the screen an example of a metaphor. Memory is a crazy woman that hoards colored rags and throws away food. Now, memory is not literally a crazy woman, nor does memory literally hoard colored rags and throw away food. But human memory does tend to remember brightly colored things that may not be of much value, vivid memories, and throw away many of the things that we might actually need. For example, you will probably remember at the end of this lecture my rather frivolous sounding example, and maybe perhaps have difficulty remembering the 5 criteria for constructing the program logic model. So this analogy, this metaphor that compares memory to a crazy woman is something that's going to stick in your head. Again, I've just done this to help you understand exactly what we mean by a metaphor, what we mean by a model. It's a simplification to represent certain aspects of the world, and we must make choices about what to keep in and what to throw out. And furthermore, the model itself is a metaphor. It stands in for the program. A metaphor is a device for seeing something in terms of something else. Kenneth Burke tells us that it brings out the thisness of a that, or the thatness of a this. In other words, a metaphor is a useful device for accentuating certain things about reality. 2 metaphors that have influenced how we see programs are the industrial metaphor, or the machine metaphor, and the open systems metaphor, which is a biological metaphor. These metaphors are very common across many endeavors of study, across many fields of study, and across many human endeavors. The machine metaphor and the biological metaphor are often used in the study of many social things. For example, if you think about something you probably learned or discussed in an introductory U.S. government course, the American Constitution, which is oftentimes presented using a machine metaphor. It's a balance of powers, gears and levers, and a kind of a machine built to produce good public policy or to produce a stable country or whatever. The biological metaphor is also often one that's used to describe many things in the social world. The biological metaphor then compares something that's not at all natural or biological to something that is biological in order to better understand how it works. So, for example, we might often talk about a country using a biological metaphor to understand that countries grow. We can talk about organizations in the same way. This open systems idea is rooted, as I said, in the biological metaphor. And although we don't usually think of programs as organisms, we attribute organism-like characteristics to programs. In fact, the very word organization that we use as a general term to talk about the agencies that run a program, that word organization is obviously related to the word organism. And they have many similarities. An organism, an earthworm, a person, a dog, is composed of many specialized parts that work together to perform some function. And we can think of a biological entity, a dog or an earthworm or a human, in the same fashion. Furthermore, when we think about this metaphor, it brings out other kinds of comparisons we might make. For example, and I'm certainly not the first one to say this, there are parts of an organism that are more important, just as there are parts of an organization that are more important. There's a hierarchical arrangement among the parts. Most biological things, creatures, can survive if they lose a limb, but cannot survive if they lose their heart or lose their head. The same with organizations. There are important parts of the organization that can be lost, metaphorically speaking, and there are other parts that are not. There are parts of it that are in control, there are parts of it that serve. So there are a number of key implications of thinking of programs as open systems and as biological systems. Programs have boundaries, just as biological entities have boundaries. We think of our skin as a boundary, the boundary of our physical self. So program boundaries, however, are almost always virtual rather than physical. But they have places where the program itself, the organization itself, stops. What is beyond a boundary? The environment in which the program exists, the environment in which the organism exists, the environment in which the organization lives, if we can extend the metaphor. Furthermore, programs have purposes. They have goals. They have objectives. This is neither the time nor the place to begin a philosophical discussion of what the purpose or an objective of a biological entity is. We could develop many arguments about that, but we can at least accept the general idea that most organisms, most living organisms, have a goal, have an objective, have some kind of purpose, if only to survive. Which brings us again to be able to make that comparison with programs and organizations. Third, the structures and functions of programs can be seen as supporting a series of means-ends relationships. What is a means-end relationship? A means-end relationship is wherein resources are consumed or converted into activities that in turn are intended as the means by which objectives are accomplished. In other words, you put something in, that something is consumed or changed, and something else comes out of the other end. Sounds a bit like a machine, but machines and biological entities have some similarities. But you can think about a biological entity that eats or drinks water. Those things are consumed, and those are turned into activities, perhaps running or stalking its prey, by which it accomplishes its intended objectives, to capture further prey, or to mate, to reproduce, whatever the objective of a biological entity is. So the same in our metaphor with programs, with organizations. Resources are put in, money, the time of the employees, photocopiers, whatever you have, those things are turned into activities that are intended to accomplish the objectives of the organization, the objectives of the program. Finally, as I mentioned earlier, programs exist in and interact with their environments, just as biological entities exist in and interact with their environments. What goes on inside of a body is just as important as what goes on outside of that body. What goes on inside of an organization is just as important as what goes on in its environment. The two things interact, they affect one another. Organizations certainly try to shape their environment, try to control their environment. Again, that's not a major topic of this particular class, but it's something to be aware of. So program logic models are a method that we use to understand all of this. A metaphorical method. Some things are put in, some things are emphasized, some things are left out, some things are de-emphasized. Program logic models are not the truth, but they help us understand reality. Program logic models, as we're about to see, are typically represented graphically. Creating a model is really about choosing a model. It is about making choices. Modeling requires choices. There are three major classifications of choices, three major kinds of decisions that an evaluator must make in creating a program logic model or choosing a program logic model. First off, the evaluator must identify things. Identify things as basically in terms of what to put in the model. Identify things that are relevant, things that are needful, things that have some utility, and what's out, things that are irrelevant or not needed. Just as the automotive engineer in creating a model of a car decides, am I trying to model the drag coefficient created by the wind, or am I trying to model the inside of the car and how comfortable it would be for a human to sit in it? You, in creating your model, keeping in mind the goals of the evaluation, must decide what to put in and what's out. As we'll see in a moment, that choice, and really none of these choices, belong to the evaluator alone. The second major choice is the classification of things. Which things belong together? For example, the program logic models included in the chapter show three very similar things: outputs, outcomes, and objectives. These things are similar. Objectives tend to be stated a bit more at the level of unmeasurable ideas, unmeasurable constructs. Outputs and outcomes tend to be stated at the level of measurable, observable variables, things you can see or feel or touch. But outputs, objectives, and outcomes are classifications of things, and they are not the same thing. Outputs are what the program does. Objectives are what we intend to achieve with those outputs. And outcomes, whether they are intended outcomes or unintended outcomes, are the observable results of the program. So we can logically distinguish between these three things. Finally, the third choice we have to make: how are classes of things connected? How are outputs, objectives, outcomes, inputs, all the different classes of things we put in our model, how are they connected? This is based on what you, as the evaluator, and others, believe the program is doing. It's based on a theory of the connection between these things. It is, in fact, the intent of the evaluation to determine if the connections you draw in the model indeed exist. Fundamentally, that's what an evaluation is about. Determining whether or not a connection exists between the program as it's implemented and the outputs that come out of it, and ultimately the objectives and the measurable, observable outcomes. Program logic models permits stakeholders, including evaluators, to classify the key parts of programs, the structures, and the processes. We classify the key parts of these programs, and we identify the key constructs for developing performance measurement systems. We identify key program results. In fact, a key reason for constructing logic models is to specify the intended causal linkages in a program. The framework that's introduced in this book, in this class, is consistent with this open systems approach. Inputs and resources are converted to results via a program process. Specifically, inputs are consumed by the program components, and implementation activities, specified by the implementation objectives, to produce outputs or tangible work done. Outputs, in turn, connect with linking constructs and outcomes. Including linking constructs is intended to encourage modelers to make these key linkages in their logic models explicit. Oftentimes, program logic leaves out the transitional steps between outputs and outcomes. There are a number of program logic models included in your textbook. In the next few slides, I will be displaying some of these and briefly discussing them. Before I begin to do so, understand this. Each of these logic models, each of these examples of logic models, features a particular program. Each one has the essential features of the logic model framework that's introduced in the chapter in this lecture. However, you are not expected to memorize these figures or any details about the programs being discussed. They are examples only. Use them to understand the types of things that go into creating a program logic model and what the finished product looks like. Again, taking a look at Table 2-1, the program logic model of Laurel House, as discussed in the book. The idea behind this logic model is to specify the causal linkages in the program. What goes in? A $10 lunch charge, a certain number of staff hours per week, a certain number of volunteer hours per week. How are those inputs transformed? How are they consumed? Well, they're transformed by the activities of the program. We have activities in and out of the house. We have people learning about their illness. Links are provided to needed services. This would be something that the staff or the volunteers do. There are goals set for the program participants. There are activities directed by the staff and the volunteer workers that enhance the peer-to-peer support networks of program members, etc. Those activities result in outputs. Again, tangible work done. Outputs are typically specified in very concrete ways. The number of clients served, the number of life skill classes, etc. Outputs then connect with outcomes. In the example here of the logic of the Laurel House, we have 3 different levels of outcomes specified across different time periods. Initial outcomes, which basically summarize how the members of Laurel House feel, how the program participants feel. Intermediate outcomes, where members engage in an ongoing development of different aspects of their life and coping skills. And then finally, the long-term outcome, the sort of ultimate output of the program. Members indicate an increased quality of life. Figure 2-1 is another program logic model portrayed in a slightly different format. But notice again, we have the similar sorts of classifications of things. Components, objectives, outputs, linking constructs, and outcomes. Notice there are some things that are not included here. Inputs are not shown in this particular form of the model. Sometimes it's not necessary to specify what the inputs are. It depends on the goals of the evaluator, the goals of the evaluation. Notice that a new concept has been introduced here, and that is program components. Many programs offer more than one component. In this particular logic model, the authors have attempted to portray the logic of one particular component of a larger program. In this case, the income supplement component. We have implementation objectives, which is also a new idea, a new concept in these models. Implementation objectives refer to what is happening within the organization. These occur before the outputs. They're more as guidance to the process of how the component works. Outputs, again, the familiar, very concrete expressions, a number of people doing this, a number of months done that. Finally, linking constructs. A very nice thing, not necessarily a required thing, but a very good thing to put in a program logic model. These, again, remember what a construct is. A construct is something that's phrased at the level of ideas, not necessarily something concrete, not necessarily something directly measurable. But these are the things that come between the outputs, the tangible work of the organization, and the outcomes, the goals that they try to achieve. So here we have people receiving supplements, the number of months, the average number of months they receive it, etc. Those things affect these linking constructs. Increase full-time employment, increase cash transfer, reduce short-term use of income assistance, which ultimately affect the outcomes. Increased full-time employment affects increased earnings. Increased cash transfer payments, money given to program participants, affects family income. It increases family income. Reducing the short-term use of income assistance by program participants improves their attitudes towards work, as do some of the other outcomes. Notice that outcomes themselves link one to the other in this particular diagram. While those tables are interesting as examples, Table 2-2 is probably the more important one for you to spend a little time looking at and studying and perhaps attempting to memorize. It contains the essential features of a program logic model. In fact, one could say that it's the model of what a program logic model should contain. Again, notice the familiar ideas across the top. Inputs, components, implementation objectives, and outputs. These are the things that happen within the organization. They're listed under the broader subcategory there of implementation. They're part of the implementation phase of the program. The program affects the environment. Looking across the bottom of the diagram there, the bottom of Table 2-2, you see on the left-hand side 4 columns of things that happen inside, more or less, the program. And then the last couple of columns, things outside the program. The outputs, in fact, are sort of on the cusp between these. The outputs sort of come outside the program to affect the environment. So in some sense of the word, they're the beginning of the linking construct idea. But they certainly are at the level of the skin of the, if we use the biological metaphor again, they're what comes out of the organization to affect the environment. And again, notice we have these intended outcomes that can be specified in the short term, the medium term, or the longer term. Although each logic model you construct will have unique features, there is a core set of features that can be identified. Each component will have at least one implementation objective. I repeat, each component, each part of the program you're evaluating will have at least one implementation objective, oftentimes phrased as to provide something, to give something, to do something, to make something. Each component then will also have at least one output. And each output will be connected to at least one subsequent program result or program outcome. Some additional rules of thumb for logic models. Constructs in a logic model cannot cause themselves. Back up for a moment and look at one of these previous things. So the constructs of increased stable employment can't cause itself. Furthermore, two-way causal arrows, while they might be conceptually useful, are a real challenge to sort out empirically. So, yes, increased earnings can affect increased family income, which affects improved attitudes towards work. And you might also argue that improved attitudes toward work cause a person to work harder, get a better job, etc., which will ultimately produce increased earnings and increased family income. But when you're drawing your model, you only want the arrows to go one way. It is possible to use two-way causal arrows, but I strongly advise against it, especially at this level of mastery. It's a very difficult thing, as I say, to sort out empirically and statistically. A final comment. Logic models are intended to be causal models of programs. As such, they are amenable to analysis as recursive or non-recursive causal models if you have the data that permits a simultaneous estimation of the strength and significance of the linkages in the model. However, we will not be doing that, learning that in this class. This is something that ultimately, if you're predisposed to going on with graduate work, perhaps at the PhD level, you might eventually become capable of. In other words, of fully modeling all of the causal linkages between these things and testing them empirically. Finally, let us briefly consider flowcharts. Flowcharts are also useful in understanding or modeling a program. However, flowcharts and program logic models are not the same thing. Flowcharts are very useful for specifying program processes in detail. They are especially useful where clients enter into a program process, are provided services, and exit the program. The flowcharts facilitate the displaying of choice points in the program process. As such, they are complementary to logic models. Logic models, however, are usually higher level depictions of program processes. In other words, program logic models do not need to specify these sort of program choice points. However, the idea of flowcharts and the use of flowcharts is very useful depending on the exact type of evaluation you're doing. For example, flowcharts indicate where possible breakdowns in processes occur, bottlenecks that create backlogs of cases. And some evaluation research is aimed at doing that. That's not the particular type we are focusing on here. But process evaluations and implementation evaluations are a special subcategory of evaluation research that focuses more on what happens inside an organization, more on the causal linkages between the inputs of the organization and the outputs of the organization. The techniques and methods and ideas we study in this class are useful for conducting that sort of evaluation, but we will not be specifically talking about those in the remainder of this class. You've reached the end of Lecture 2-1, Understanding and Applying Program Logic Models. If you feel you've understood the concepts discussed here, I advise that you proceed to Lecture 2-2, Constructing Program Logics in Program Evaluations.